Hi, in this video, we are going to talk about electron configuration of atoms. Now, what is electron configuration? Well, it tells us how the electrons are distributed among the available subshells for a particular atom. Now, in this video lesson, we are going to talk about the electron configuration associated with the most stable state of the atom. In other words, it is the lowest energy level of the atom. In quantum mechanics, this is called the ground state. Chemical properties are related primarily to the electron configuration of the ground state. Now let's take a look at the electron configuration for the ground state hydrogen atom. For hydrogen atom, the electron configuration is 1s1. Now 1s refers to the atomic orbital in which the electron is located. Alright? And the superscript refers to the number of electrons in this orbital. Okay? In other words, electron configuration tells us that hydrogen's single electron is in the 1s orbital. Now, any other configuration associated with energy levels other than the lowest is called the excited state. Now, how do we go about writing an electron configuration for the ground state of an atom? The first thing we need to know is the ordering of the atomic orbitals based on their energies. Now, let's take a look at the energy levels for the ground state of the hydrogen atom. Each orbital is indicated by a dashed line. 1s is the lowest energy available. The next energy level is 2s and 2p. Do note that even though s and p are different in shape, they both have the same principal quantum number, which is n equals to 2. This implies that they have the same energy. The same logic applies to the atomic orbitals belonging to the n equals to 3 and n equals to 4 energy shell. However, things get a bit more complicated for multi-electron atoms because of electron-electron repulsion, as a result of which subshells within the same principal shell no longer have the same energy, unlike the one-electron system. For example, 2p and 2s no longer have the same energy. In fact, 2p is higher in energy than the 2s. Likewise, 3p is higher in energy than the 3s. Another interesting thing to note is that in elements other than hydrogen, the energy ordering is not determined by the principal quantum number alone. Now, why do we say that? That's because in many electron systems, the 4s energy level is lower than the 3d. Likewise, the 5s is lower in energy than the 4d. Now let's go over the rules of filling the atomic orbitals with electrons. Rule number 1 is called the build-up or the Aufbau principle. According to this rule, electrons will fill orbitals from the lowest to highest energy. However, sometimes if there are two subshells of nearly the same energy, the build-up order is determined by the overall energy of the atom rather than the energy of the subshells alone. This is the filling order based on the build-up principle. As mentioned before, electrons will fill in the lowest energy orbital first, which is the 1s subshell. And after filling in 1s, then they will move to 2s, then 2p, 3s, 3p. But before the electrons fill in the 3d orbital, they will first occupy the 4s orbital because it is lower in energy. And then they will go to the 4p, 5s, and so on and so forth. Now, in order to write down the electron configuration of the ground state of any atom, you need to require to know this filling order. Now, before we move to rule number 2 of filling in atomic orbitals, we need to know something about electron spin. Electrons act as if they were spinning on its axis, and because the electron is charged, this spin gives rise to a circulating electric charge that consequently generates a magnetic field. It's as if the electron is behaving like a bar magnet. Now, in presence of an external magnetic field, there are two possible orientations of the spin that have been observed. One is the spin-up configuration, which has been assigned the spin quantum number of +½ The other is a spin-down configuration, the spin quantum number of which is assigned as -½ With this knowledge of spin, we can now move to rule number 2, which is the Pauli's exclusion principle. Now, according to this principle, no two electrons in one atom can have same 4 quantum numbers. So what's the consequence of this principle? It means that within one orbital, electrons must have opposite spins. It also means that an atomic orbital can have a maximum of 2 electrons with opposite spins. So let's see how many electrons can be accommodated in the different subshells in an atom. So let's start with the S subshell. Now, S subshell has only one atomic orbital. So based on the Pauli exclusion principle, it can hold a maximum of 2 electrons. Now let's move to the P subshell. In the P subshell, there are 3 orbitals available. And since each orbital can have 2 electrons, so the maximum number of electrons in a P subshell will be 6. Likewise, a D subshell has 5 orbitals. So the maximum number of electrons in a D subshell would be 10. Finally, we have the F subshell where there are 7 orbitals. So the maximum number of electrons is going to be 14. So therefore, we see that each orbital can hold a maximum of twice as many electrons as the number of orbitals that are available in its subshell. Let's try out few examples. Write down the electron configuration for the following elements in their ground state. Let's start with magnesium, whose atomic number equals to 12. Now, based on the build-up principle, electrons will start filling in from the lowest energy subshell, which is the 1s. So let's write down 1s. Now, based on Pauli exclusion principle, an S subshell can have at most 2 electrons. So we write this as 1s2. Now, the next 2 electrons will go to occupy the 2s subshell. And then they will occupy the 2p subshell. Remember, a p subshell can have a maximum of 6 electrons. So it's going to be 2p6. So now the remaining 2 electrons will go to occupy the 3s subshell. So therefore, the electron configuration of magnesium is 1s2, 2s2, 2p6 and 3s2. Alright? Now let's do the same for scandium, whose atomic number equals to 21. So we start putting in electrons from the 1s subshell. So let's do that. So we have 1s2, then 2s2, 2p6, 3s2, 3p6. And now let's pause for a moment. Because the electrons, before they occupy the 3d orbital, they are going to occupy the 4s subshell, which is lower in energy. Alright? So the next 2 electrons will go in the 4s subshell, and then the remaining electron will go to occupy the 3d subshell. Alright? Now you can also rewrite this as 1s2, 2s2, 2p6, 3s2, 3p6, 3d1 and 4s2. But just remember that the electrons will occupy the 4s first before they occupy the 3d. Here are the ground state electron configuration for elements with atomic number ranging from 1 to 36. What I would like you to note are the electron configurations of the noble gases which have completely filled subshells. Now, why do we care about the noble gas configuration? Well, that's because there is something called the noble gas core notation. For elements beyond neon with many subshells, it's convenient to abbreviate the electron configuration with symbols for noble gases in brackets. For example, let's write down the electron configuration for sodium. Now, the atomic number of sodium is 11, so the electron configuration will be 1s2, 2s2, 2p6 and 3s1. Now, do note the electron configuration for the first few subshells of sodium is identical to that of neon. So instead of writing the full electron configuration, we can rewrite this as neon 3s1. That means we are writing the symbol of the noble gas in brackets followed by the remaining configuration. Now let's go back to our previous examples. We are now going to rewrite the electron configuration for magnesium and scandium using noble gas core notation. So let's start with magnesium, which has electron configuration of 1s2, 2s2, 2p6, 3s2. Now the electron configuration for the first few subshells up to 2p is same as that of neon. So we are going to rewrite this as neon 3s2. Alright, let's do the same for scandium. Now for scandium, the electron configuration of the subshells up to 3p represents that of argon. So we are going to write this down as argon 3d1 4s2. Before we end this video lesson, let's talk about a few exceptions to the above or the build-up principle. Consider the electron configuration for chromium whose atomic number equals to 24. Now based on the build-up principle, the configuration for chromium should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d4. However, the actual configuration for chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d5. And do note that with this configuration, chromium has a half-filled d subshell. Alright, now let's consider the case for copper. Copper has an atomic number equals to 29. Now again, based on the build-up principle, the expected configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d9. However, the actual configuration for copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d10. Okay, now with this configuration, copper has a completely filled d subshell. Okay, so why is it so? Now this happens when the 3d and the 4s orbitals are close in energy, and also when the atoms have the choice to obtain a half-filled or a completely filled d subshell, which gives it more stability. Now recall that when we talked about built-up principle earlier, I mentioned that we need to consider the total energy of the atom in certain cases rather than the energy of the subshells alone. Okay, With this, we come to the end of this video lesson, and thanks for watching this video.